Everybody, I want to talk to you today about how to simplify radicals. So let's go. So what I've got here is so I'm assuming you know what square roots are, but let me talk about what the definition is, like what the formal definition is. So if I have the nth root, and I know this looks kind of like an r, that's an n, I promise. The nth root of some number k is whatever number that if I raise it to the nth power gives me k. So in other words, something like the square root of 4. Oh, and by the way, let me get a couple of terms out of the way. The radical is this sign, is this symbol here, the square root symbol. This number n is called the index. So if I refer to the index, that's what I'm talking about. And I usually won't call it this, but this thing is called the radicand, if you needed to know that name. So the first thing I want to establish is that even in odd indices work differently with respect to negative numbers. With respect to positive numbers, they were pretty much exactly the same. However, with respect to negative numbers, they do different things because of what raising a negative to an even power does versus raising it to an odd power. So I'll explain that in case you haven't seen that explanation before. I'll explain that in a little bit. But for right now, let me just say this. The square root of 4. Oh, and by the way, if there's no index written, it is secretly a 2. So this is a square root here, and this is a third root here, obviously. So the square root of 4 is 2 because 2 times 2 equals 4. So that means that this guy has to be 2. The square root of negative 4 is not a real number. It's a complex number because if I raise, so the obvious first guess there is negative 2, right? What if I did negative 2? Negative 2 times negative 2. Well, the two negatives multiply together and cancel out and gives me 4. So that one doesn't work. 2 obviously doesn't work. So what options do I have left? And the answer is there aren't any. There are no other real numbers that make this work. So not real. Complex numbers were invented to solve this sort of problem, but we're not going to get into those in this class. On the other hand, the third root of 8 is 2, because 2 times 2 times 2 is 8. So that works pretty much exactly the same as the square root version, but the third root of negative 8 is negative 2. That's totally fine because minus 2 times minus 2 times minus 2 is negative 8. Because these two negatives cancel out and become positive, but that leaves me an extra negative left over to make the negative 8. So basically what happens is you can take the square root of positive numbers, but not negative ones. And you can take the third root of positive numbers or negative ones. So in general, even roots work differently and more confusingly than odd roots. Odd roots work great. They're very smooth and easy. You don't have to worry about the negatives at all. Nothing goes wrong with them. Even roots, you have to worry about negatives, because even if you have, like, if I did the fourth root of negative 16 here, that would also be not real, because any even set of negative numbers that you're multiplying together, all the negatives cancel out. And so you can't make a negative out of an even number of negatives. You get a positive number. So that's why square roots and cube roots, and basically in general, even roots and odd roots behave differently, is because you can't multiply an even number of negatives together to get a negative. If you do, you get a positive number, and so you can't make a negative even root. So variables work a little bit differently with even roots, but pretty much exactly the same with odd ones. In fact, let me go over here for a second. I should have done this page first, I think. So I want to look at these examples first. So if I'm taking the square root of negative 3 squared, well, negative 3 squared is 9. So this is the square root of 9. Well, the square root of 9 is 3. So when I have this negative 3 in here to start, I end up with a positive 3 at the end. So if I'm doing something like the square root of x squared, that doesn't just cancel out. What you get is the positive version of whatever you put in. Now, if it's positive to start, that's fine. It remains exactly the same. But if it's not positive, if it was negative to start, like this one was, then it becomes positive, like this 3 did. So our function that says if something is positive, leave it alone, and if it's negative, make it positive, is absolute value. So if you're taking the absolute value of some even power, or excuse me, the absolute value, if you're taking the even root of an even power, you don't get the thing you started with, you get the absolute value of it. On the other hand, if you do this with an odd root and a negative number, I have the third root of minus 3 to the third. Well, minus 3 to the third is minus 27. So this is the third root of minus 27, which is negative 3. So the thing I started with was the thing I ended with. Great, that's easy. Third roots and odd roots in general are actual inverses of each other. They just cancel. They just cancel with powers. So third power, third root cancel out. So the third root of x cubed is just x. So watch out for this. When you're taking even roots are a pain. They're just a pain. Like, you have to watch out for the negatives. You need absolute values. You have to be really careful. Odd roots are great. They work fine. There's no need to sweat the negatives. Everything's easy. So odd roots are great. Even roots, beware. It's very easy to make small errors there. So in general, if I have the square root of x squared, that's absolute value of x. Fourth root of x to the fourth, also absolute value of x, because 4 is even as well. Third root of x to the third, no problem, just x. Fifth root of x to the fifth, just x. Okay, so watch out for your even roots of even powers. Odd roots of odd powers, you're home free, easy times. Even roots of even powers, watch out, you need absolute values. Okay, here's what we're actually going to do in order to simplify radicals. We are going to use this property right here. We're going to split up our radicals. So if I have the nth root of two things that are multiplied together, I can split it up into the nth root of one times the nth root of the other. So in other words, I can break up my my radical over multiplication. And it turns out over division as well, which we'll talk about when we get there, but it works just the same. And you might say to yourself, well, how am I going to use this to help me with that? And the answer is, we are going to write this in such a way that we're going to split it up into something that simplifies nicely and all the rest of the crud that's in there. So here's what I'm going to do. I'm going to do a factor tree for 56. And in general, you're going to want to do factor trees for all your numbers. And in fact, the variables are significantly easier to deal with than the numbers, because with the numbers, you have to figure out what the exponents on all of them are, and I'll show you why. So 56, let's 2 times 28, and this is 2 times 14, and this is 2 times 7. So I want to write this as 2 to the third times 7 square root. The reason I want to do that is that I want to take this and split it up into things that are pairs or any even powers, and then everything else. And the reason I want to do that is that the square root of 2 squared here is 2. So that just simplifies nicely, and I can drop that part of the radical if I split it up right. So I want to write this as 2 things. So this is all the stuff that simplifies. And I'll talk about what that means in a second. Oh my God, my writing, I'm sorry. Other junk. And I actually think of this one on the right as like the junk pile. That's where everything goes that can't be that can't be simplified nicely. So the 2 to the third, what I'm going to see here is that the square root here, the index, this hidden 2, is telling me that I'm going to end up dividing all the powers by that. The reason we're going to do that here, let me go over here for a second. spend a little bit of time. So if I have like the square root of, let's say, x to the 8th, I can think of that as the square root of x to the 4th squared. Well, and squared and the square root cancel out. Right, absolute values because it's an even power. I know you probably realize that x to the 4th has to be positive, but just to be consistent here, absolute values because it's even power, even root. And so when I have this square root here, this index of a 2, that's going to cancel with some power of a 2. Well, any even power can be written like this, right? Just using the rules of exponents. If this was x to the 500th power, I could write it as x to the 250th times to the 2nd, right? And then the square root and the square cancel. Similarly with, 5th powers, I have fifth root of, let's say, x to the 75th power. I can write that as x to the 15th to the 5th, fifth root of that. And those things cancel, right? And so you can see, that cancels too. And so you can see that what's happening is I'm effectively taking this and dividing by 5 when I sort of factor the 5 out so that I can cancel it with the radical. So that's one way to think of it, is that I'm dividing the power by that number, or by the index. So if I have something like 56, like the square root of 56, which we're going to go simplify in just a second, this 2 here is what I'm going to be dividing the powers by. So if I break this up into all the even powers and all the stuff I have left over, right, because it was 2 to the 3rd times 7, then this will cancel and simplify, and then this won't. Right, that'll just be all the junk left over that didn't simplify, and that's my goal. That's basically the strategy. So let's go back and look at this. Right, so all the stuff that simplifies. Well, I have 3 2s. Okay, so if I had 2 of them here, that would simplify. And then all the other stuff left over that I don't have at least 2 of goes in there. This cancels. 2 times 7 is 14, and the thing that I get is 2 times the square root of 14. There's nothing under this radical here that can cancel anymore because I put it all over here and then just canceled it and just simplified the what's inside the radical. And that's what I'm going to do here too. All right, so I want to do that in a slightly more complicated setting. So 16, now notice that I have a 3 here, so now I'm looking for multiples of 3 because I want to divide my powers by 3. So 16, let's go up here. Now I guess I can do it here. 2 times 8, 2 times 4, 2 times 2. So this is the 3rd root of 2 to the 4th, x to the 5th, y. And notice that the variables are actually easier to deal with because the exponent just tells me how many I have, right? The first thing I have to do with numbers is figure out how much of everything I've got by doing this. So I'm going to break this up into all the things that are multiples of 3, all the powers that are multiples of 3, and everything else. So I have 4 2s, so I'm going to take 3 of them and put them over here. And then the one remaining 2 is going to go over there. I got 5 x's, so I'm going to take 3 of them, put them over here, and the remaining 2 x's are going to go over there. I have 1 y, so I don't have enough to put anything under the left radical, so that's just junk, and it goes over here. Well, the 3rd root of 2 to the 3rd x to the 3rd, when I divide all the exponents by 3, is 2x. And then all this other stuff doesn't simplify, because anything that's simplified, I put under the left radical. And that's it. That's the basic idea. We want to use this property to split our radicals into 2 pieces. One of the pieces will have all the stuff that simplifies nicely. The other piece will have everything else. The piece that simplifies nicely, we simplify that. Everything else, we just leave alone. There's nothing we can do with it because nothing else simplifies. So let's see a couple more examples. Right, so some messier ones. All right, so 6 times the square root of 50. Here's what you're going to notice about something about a number like this. That 6 doesn't do anything for most of the problem. At the end, it multiplies, but that's it. I'm just looking at the root 50, right? So the 6 is basically extraneous. It kind of goes along with every step, and then gets tacked on at the end. So 50 is 2 times 25, and then 25 is 5 times 5. So this thing is really 60, or 6, excuse me, times the square root of 2 times 5 to the second, which we're going to break up into 2 pieces, right? 5 to the second, because that simplifies nicely, and then the one remaining thing is the 2. Square root of 5 to the second is just 5. Those cancel, and I end up with 6 times 5. Oop, that's an ugly times. Square root of 2. 6 times 5 is 30. 30 root 2. That's it. You literally just split up the radical. Don't even do anything with any coefficients that you see outside of the radicals until the very end, when like right before you box your answer. Just multiply it into the coefficient that's outside the radical. All right, so something very similar, third root of 40x cubed y to the 7th z to the 5th. All right, first thing is first, we got to figure out what 40 is composed of, like what. Here, I'm gonna move this a little bit so I have some more room. What numbers go in to make up 40? So we are going to do a factor tree like always. I'm going to go with my pencil. There we go. So 40 is 2 times 20. 20 is 2 times 10, and 10 is 2 times 5. So I've got 2 to the third times 5. So this is the third root of 2 to the third times 5 times x to the third, y to the 7th, z to the 5th. And I'm going to break that into 2 pieces. 2 to the third, well, I've got 3 2's. That's how many I'm looking for, right? I'm looking for multiples of 3 here. 5, I only have the one 5, so that has to go over here. I got 3 x's. Those all go here. I've got 7 y's, so I can put 6 y's over here, not just 3 of them. And that leaves me 1 to go over there. And then z to the 5th, I can put 3 z's here, and that leaves me 2 z's left over there. Over on the left, all of my variables, or all of my powers, are multiples of 3, which is how I arranged it, of course. So we just divide them all by 3. So we get 2xy squared z. And over here, we don't do anything. We just leave it. 5yz squared. And I'm done. So third root, all these things should be multiples of 3. 11th root, they should all be multiples of 11, right? So what we want is when I divide by 3 here, that I don't have any remainders left over, right? All of these have to be multiples of whatever that is. So you just take as many things, or as many of each of the numbers and variables, and put them under here as you can, and then whatever's left over that would not make it a multiple of whatever the index is just goes in the junk pile, and the junk pile just kind of sits there. There you go. That's simplifying radicals. So there's one other thing I want to mention, which is what to do with fractions. And fractions work the same as numbers that are being multiplied. So the nth root of a over b, you can split up radicals over division as well. So it's nth root of a over nth root of b. So something like this, the square root of 27 over 4, I can split that up into the square root of 27 over the square root of 4. And that's useful because square root of 4 is 2, right? I don't need a radical there. I can just write that as 2. Square root of 27, we can simplify. So 27, 3 times 9, that's 3 times 3. So I got 3 to the third. So this guy here is the square root of 3 to the third over, I'm just going to write that as 2. The square root of 3 to the third is square root of 3 squared. I'm doing the same thing as I did before, giving myself 2 radicals, one of which, so square root of 3 squared is 3, root 3, we don't touch. So this is 3 root 3, 3 root 3, not 3 root 2. Try that again. 3 root 3 over 2. So you can split things up. or you can split radicals up over division as well as multiplication. Sometimes it's better to simplify first. Maybe I'll do another example. I don't think I have one planned for that. I want to show you what to do in a case like this. A little line here. I want to show you what to do in a case like this, and then we will do. I'm going to do one more where you want to simplify first. So 7 and 10, not going to touch them. I'm just going to work on square root of 75. And in fact, I'm going to go off to the side and do that one separately. All right, so 75 is 3 times 25, which is 5 times 5. So square root of 75 equals the square root of 5 squared times the, let's back up a second there. 3 times 5 squared, which we split up into 2 pieces. The nice stuff that doesn't get simplified, 5 root 3. And so this 7 times the square root of 75 all over 10 is 7 times 5 root 3 over 10. And of course, the 10 and 5 cancel. And so what I end up with is 7 root 3 over 2. So don't forget your fraction rules. They all work the same. Nothing's particularly different about them in radicals. Just simplify your radicals first and then cancel afterwards. Do I have another page here? Yes. So we're going to do this. So let me do one more like this. So if I have like the square root of, oh, what do we want to do here? Like 18 over 98. Right. So that it's really tempting to do this. But I wouldn't do that. The first thing I want to do is simplify under the radical. If there's stuff you can cancel under there, cancel it, because that's going to make your job easier, at least in general it will. So those are both even. So what I'm going to do is I'm going to write that, and instead of splitting up the radical right away, I'm going to write it as the square root of, when I pull a 2 out, I get 9 over 49. And now this is easy. Right, it all works out nicely. So in general, you can split radicals up over division, of course, right, like this. But before you do that, see if there's anything that cancels. Now, I didn't mention it here, but there's nothing that cancels, right? It's all 3's in the top and all 2's in the bottom. So nothing cancels there. But in general, see if you can cancel stuff first, because that'll probably make your job easier. Almost always does. Canceling is usually a good first step. All right, let me pause for a second. I think that's all I wanted to say. I just want to go look at my list and make sure. Yep, I had all the major points, so I am good to go. I'm going to go ahead and stop the video, and I will see you guys in the next one.